Okay, class 12. One last video on capacitors I wanted to upload. Okay, so this thing is called combination of capacitors. Okay, you are actually very familiar with this topic because in class 10 itself you've done something called combination of resistors. Okay, wherein you had two combinations. One was the series combination of resistors and the other was parallel combination of resistors, of course. Okay, so this was resistor number 1, resistor number 2, resistor number 3. Okay, so R1, R2, R3. All right, now in series combination, one thing that was same for all these three resistors was the current flowing. In these three resistors the current flowing was the same. All right, of course the potential difference across, since they have different resistances, the potential difference was different, but the current flowing was the same. In parallel combination of resistors, just to give you a reminder, okay, just to remind you all, okay, the thing that was same for all the three resistors was the potential difference. Okay, the potential difference, since they are connected to the same 2 points, all three resistors are connected to the same 2 points. Okay, so the potential difference to each across each of these resistors was the same. All right, so the same thing is true when it comes to capacitors. So first of all, we are going to do series combination of capacitors, okay, and you all will do the parallel combination of resistors as d by t. Okay, d by t is parallel combination. Okay, happy d by t-ing. Okay, so series combination. So I have a capacitor whose capacitance is C1, which is connected to the second capacitor having capacitance C2, which is connected to the third capacitor having capacitance C3, whose second plate is connected to the ground. Okay, so what happens is, say for example, I give plus q amount of charges to the first plate of the first capacitor. What happens is minus q is going to get induced in the inner wall of the second plate. Okay, outside plate gets induced plus q. Now this plus q being a free charge, okay, minus q is the bound charge, plus q is the free charge. It's simply this plus q, it flows to the first plate of the second capacitor. So you have plus q over here, you no longer have plus q here. Okay, so plus q. Now this plus q is going to induce minus q and plus q on the outer side. Now that plus q being a free charge, it simply flows to the first plate of the third capacitor. So plus q, it is going to induce minus q on the inner walls, and of course it is going to induce plus q on the outside wall, outside plate. Okay, so this plus q being a free charge, it simply flows to the ground. So what we basically have is, we have equal amount of charges. Okay, so the first capacitor also holds q amount of charge, the second capacitor also holds q amount of charge, the third capacitor also holds q amount of charge. All three capacitors, they hold the same amount of charge, which is q. So the charge that is held by each of these three capacitors is the same. Okay, so charge held by the capacitor is the same. Like in case of series combination of resistors, the current flowing through the resistor is the same. Okay, the charge held by the capacitor is the same in this case. All right, now this is point A, this is point D, as you can see in the picture. So the potential difference between points A and D is V. I'm saying the potential difference between these 2 points A and D is V. So that V will be the sum of V1 plus V2 plus V3, where V1 is the potential difference across the plates of the first capacitor. The charge is Q, its capacitance is C1, so the potential difference is V1. The charge is Q, but its capacitance is different, C2, so the potential difference will be different, which is V2. The charge is the same, but the capacitance is different, C3, so the potential difference will be different, which is V3. Okay, so V, the potential difference between points A and D, will simply be V1 plus V2 plus V3. Or V is, instead of V1, I will write Q by C1, because we know Q is equal to CV. So V is Q upon C. So from here, V1 is Q upon C1. There's the potential difference across the first capacitor, Q by C2 and Q by C3 likewise. Okay, now instead of these three capacitors, instead of the three capacitors, say for example, if we use a single capacitor, such that this is grounded. Okay, this is a symbol for connecting it to the earth, such that when we give this capacitor q amount of charge, the potential difference that is generated across the two plates, say for example, is V. which is the same as the potential difference across points A and D. So what I'm saying is, if we give, this is a special kind of a capacitor such that when we give it Q amount of charges, the potential difference that is generated across this is the same as the potential difference across points A and D across these three capacitors put together. All right. Now that kind of a special capacitor, okay, to which when we give Q amount of charges, its potential difference becomes V. This capacitor has a name. It is called an equivalent capacitor, remember. So what is an equivalent capacitor? An equivalent capacitor is 1, okay, to which when we give Q amount of charges, the potential difference generated across its two plate is the same as the potential difference across all these three capacitors put together. All right. So what I've written is, now if we replace the three capacitors by an equivalent capacitor such that when the same charge Q is given to the capacitor, all right, equivalent capacitor, the potential difference between its plate is V, okay, then for this equivalent capacitor we have V is equal to Q by C, where C is the capacitance of the equivalent capacitor. Okay, this is for the equivalent capacitor, remember. All right, this is true for only for an equivalent capacitor, remember. This is not true for any general capacitor. Okay, this won't be true for any general capacitor. This is only for an equivalent capacitor, such that when we give it the same amount of charge, the potential difference developed is the same as between points A and D, remember. This will be true only for an equivalent capacitor, remember. This is a very, very important point that you need to write. You have to write this, remember, if you are given this derivation. So for the equivalent capacitor, we have V is equal to Q by C. This is my equation number 2. This is my equation number 1. So from equations 1 and 2, what we can write is, you can see the left hand side is the same, okay, so we equate the right hand side. So from equations 1 and 2 we have Q by C is whatever and blah blah, therefore 1 by C is 1 by C1 plus 1 by C2 plus 1 by C3. So this is the expression we get for combination of capacitors in series. Okay, now if you look at this equation, it looks very similar to this equation that you know, 1 by R is 1 by R1 plus 1 by R2 plus 1 by R3. Only thing is, this was for the parallel combination of resistors, okay, but this is, in case of capacitors, this is for the series combination of capacitors, remember. All right, now without mentioning, I think you understood that for parallel combination of resistors, the equation that you should be getting is C is 1 by C1, sorry, let me write CS for series. There's the equivalent capacitance for series, C1 plus C2 plus C3. Okay, all right, let me do one thing. Instead of C, let me write CS to be the capacitance of the equivalent capacitance series. So Q by CS. So Q by CS is this much. So 1 by CS is 1 by 7. Just to let you know that this is for series combination of capacitors, CS, 1 by CS. Okay, now and one more thing I want to stress upon. Say for example, if C3 is the smallest of between C1, C2 and C3, say for example C3 is the smallest capacitance, C1 say for example is the biggest, C2, then after C3. So C3, the third capacitor has the smallest capacitance. Okay, C3 is the smallest. So from this expression, can I write 1 upon CS is greater than 1 upon C3? Okay, since 1 upon CS is the sum of 1 by C1, 1 by C2 and 1 by C3, so therefore 1 by CS has to be greater than 1 by C3, or therefore C3, okay, is greater than CS. C3 is greater than CS. So what we get to see is, in series combination, the equivalent capacitance is smaller than the smallest capacitance that we had. It is smaller than C3 also. C3 was the smallest, so the equivalent capacitance of series is smaller than the smallest value of capacitance that we have. Okay, this is the same when we speak about parallel combination of resistors. Okay, if R3 is the smallest, then 1 by R is greater than 1 by R3. So R3, okay, is greater than R. Let me call it RP. So parallel combination of resistors, the parallel equivalent resistance is smaller than the smallest value of resistance that we have. Okay, that is why all household wirings, it's done in parallel, because it basically reduces the effective value of resistance. So everything is done in parallel. Okay, so likewise the equivalent capacitance in series is smaller than the smallest value of capacitance that we already have. Okay, so I think this much is all for this video. Okay, we do for the video. And don't forget, parallel combination of capacitance is a DYT. I always give this topic as a DYT, so I hope you'll do this. Okay, stay safe and take care, all of you. Thank you.